I'm Eva, and I will present you our work on appearance modeling for Radiance reconstruction. So the goal of 3D reconstruction techniques is to enable novel view synthesis, meaning that we can put the camera in arbitrary pose and render realistically looking view. To achieve high-quality reconstruction, we start with a set of images captured from different viewpoints and their camera poses. And then we optimize the parameters of underlying scene representation in order to get realistically looking 3D model. There are several alternatives to get 3D reconstruction. Some are implicit, like nerve-based methods, which use neural networks to learn continuous representation of a scene. Planoxis-like methods replace the neural representation with voxel grid, enabling faster rendering. And finally, primitive-based approaches represent the scene as a collection of optimized primitives and rasterize it in order to get a final image. So, in our work, we focus on primitive-based approaches because unlike neural representations, they model the appearance explicitly. For the appearance model, 3D-GS uses a set of view-dependent basis functions, most commonly spherical harmonics, and higher degrees of spherical harmonics capture finer angular details. However, in practice, primitive-based radiance methods use only low degrees, which limits their ability to model view-dependent effects, which is visible in modeling effects such as reflections on car windshield or specular highlights. I think I said that. Okay. So our motivation is to find more expressive and compact appearance model. Instead of approximating view-dependent appearance with a fixed set of basis functions, we want to look into parametric functions, and several other approaches were already proposed, like spherical betas, which use the isotropic model which has bounded support, or spherical Voronoi, which splits the sphere into Voronoi cells to represent directional variations. So although these methods demonstrate that learned appearance model can outperform spherical harmonics, they seem a bit ad hoc. And we were more interested in actually figuring out which properties of those functions makes a good appearance model. So in our work, we first evaluate a wide range of spherical functions, then we identify the properties that make the appearance model successful, and then finally we design a representation that is both computationally effective and able to accurately capture the angular details. So, to better analyze the behavior of different appearance kernels, we decompose the color into diffuse and specular part, and the diffuse part is modeled by one scalar per RGB color, and then the specular component is modeled by the mixture of parametric kernels. So we study the spherical functions in a way that we group them in 3 families. And first one is isotropic kernels, which are rotationally symmetric, like spherical Gaussians or spherical betas. The second family consists of ring-like functions and multimodal kernels that are able to split unimode into multilobes and model more complex signals. And finally, we consider anisotropic kernels like linearly transformed cosines or anisotropic spherical Gaussians. So overall, we collected 10 different kernels from directional statistics and graphics, and now we want to evaluate them as a candidate appearance models for novel view synthesis. Our objective was to assess the practical ability of the kernels to model view-dependent appearance, since real-world scenes contain more complex lighting interactions than synthetic setups. They provide a much more challenging benchmark. So for this reason, we evaluate the kernels on MIPNER 360 dataset consisting of real-world data. And we evaluate reconstruction quality using different metrics like SSIM, PSNR, LTAPFs, and FLIP. But for this work, I will just show the result with PSNR. And we also examine the trade-off between the reconstruction quality and compactness. So in our first experiment, we will identify the desirable kernel properties. Next, we will investigate how using single lobe versus multiple lobes affects the optimization stability and their modeling power. And then we study the impact of kernel normalization on reconstruction quality and optimization stability. And finally, we explore regularization strategies for the multi-lobe setting to encourage diversity between lobes and improve overall performance. So in the first table, we will see PSNR against compactness. And as a first step, we evaluate spherical harmonics. Each dot corresponds to the degree of basis used in the evaluation. Even if we evaluate, isotropic spherical kernels, we see that even though they take much less parameters, they outperform spherical harmonics, showing that even simpler trainable kernels provide more expressive appearance model. Then we evaluate ring-like and multimodal kernels, and our results show that multiple peaks don't need to be disentangled. Instead, single multimodal kernel can capture them effectively, and we can save some memory. And finally, we evaluate anisotropic kernels, which provide to be the most expressive family and consistently achieve the best reconstruction results. So here it's visible that in multi-lobe setting, the returns are diminishing. So we would focus more on constructing more powerful model instead of combining many simple lobes. However, you may notice that one of the kernels perform worse in two-lobe setting than in single-lobe setting. And this behavior stems from the fact that this kernel is not normalized, which leads to our next experiment, in which we compared normalized and unnormalized spherical kernels. And on the graph, you will see the gap between function performance without and with normalization. So the normalization ensures that the energy of a function is constant under varying parameters. And for some spherical kernels, computing the closed form solution may not be possible or be expensive, which means it's impractical. So despite that, our experiments revealed that normalization actually plays a crucial role. And across all kernel families, normalized kernels consistently outperform their unnormalized counterparts, with performance gap being even more pronounced in multi-lobe setting, where the optimization landscape is considerably more challenging. Okay, and finally, we investigated whether we could further improve performance in the multi-lobe setting by regularizing the lobes using the Wasserstein distance, which is optimal transport metric that measures the distance between the spherical distributions. And our idea was by encouraging diversity among the lobes, we could avoid them collapsing into the same shapes, which can be the case. And the figure shows that contribution of each lobe for every primitive. Without the regularization, most primitives have similar functions as indicated by darker color of the spherical Wasserstein distance between them. And after introducing the regularization, the distance between the lobes increases, which is reflected by the brighter colors and indicates greater diversity. However, we also observed that with increased diversity, the additional lobe collapses instead of learning a complementary representation, and as a result, the reconstruction quality does not improve, and the representation degenerates to a unilobe setting. So, summary of the findings, we would like our appearance model to be anisotropic, multimodal, and have efficient normalization. And based on these findings, we set out to develop a better appearance model. We start with normal anisotropic spherical Gaussian, which we took from the path guiding field, and we chose it as base for our function since it was top performer in the evaluation, and it was anisotropic and had a closed form integral. And now we thought how we can add the multimodality to it. So one option was to think about this like adding the axis of symmetry and splitting the lobe into two modes, but we decided to go for something else, and we looked into recent works on harmonic appearance models in reconstruction and rendering, like neural harmonic textures, and we decided to do it through the addition of harmonic modulation. So the first part is normalized anisotropic spherical Gaussian, which is represented by this part of the equation, and it allows us to introduce the anisotropy, move function around the sphere, and change its intensity. And the Gaussian envelope is then combined with harmonic carrier, which controls the number of oscillations around the sphere. And this component gives the kernel its multimodal behavior. We derived the analytical derivatives and implemented them in CUDA, so it's easy and fast to evaluate in both forward and backward pass. And here are the results. So we evaluated our kernel. For that, we selected some scenes containing strong specular reflections and compared the rendered results with those produced with spherical harmonics, which are visible here. Okay. And to highlight the differences, we visualize error using flip maps. In these maps, brighter color indicates the larger difference between the rendered image and ground truth. And as we see, our kernel consistently produces lower reconstruction error than spherical harmonics, particularly in regions with strong specular reflections. We also compared our method with existing state-of-the-art appearance models, including spherical beta and spherical Voronoi. And our kernel achieves the most realistic reconstruction of the view-dependent effects while being more compact than spherical Voronoi. And the results are, compared to spherical harmonic and spherical Voronois, our appearance model is 4 times more compact, at just 12 parameters per primitive. It achieves 11% better mean squared error than spherical harmonics, and it is more efficient. It trains 1.3 times faster than spherical harmonics and achieves approximately 10% faster interference, which is mainly due to reduced memory traffic. Finally, our explicit decomposition of appearance allows it to split it into diffuse and specular components, which provides additional advantage because these components are represented separately. We can render the scene using only diffuse or only specular contribution, which opens up exciting possibilities for future work, such as independent editing of scene lighting or as a prior for intrinsic decomposition. And of course, introducing such a flexible parametric appearance model comes with some trade-offs. They are more vulnerable to overfitting to the training views. In practice, it makes the choice of optimization parameters a bit more challenging. And in contrast, spherical harmonics are frequently limited by their degree. So although it limits their ability to produce sharp view-dependent effects, it acts as implicit regularizer and produce oversmoothed interpolations. So looking ahead, we think that our work opens several exciting research directions, and it allows for relighting, HDR imaging, path guiding, and environment map fitting. So if you would like to see more about our project, we created a website where you can play with the kernel and see more of the results. And here's the QR code where you can see the project. Okay, so on the final note, I'm a master's student. I was a bit stressed giving this talk, but I think you can tell. But if you think, like now I'm looking for an internship, and if you think that I could be a nice collaborator for you, please reach out to me. Thank you very much.
So we have time for a few questions here.
Hello, thank you for the presentation. It was very nice. I was wondering, in Gaussian splatting with the spherical harmonics, sometimes the view-dependent effects are not encoded in the spherical harmonics, but actually on some Gaussians, like behind the surface, that when you look at them for certain points of view, like create the view-dependent effect. Yeah, I was wondering if like that kind of behavior also happens with your approach, or it doesn't, and if you have any insight on that.
But okay, I think I didn't fully understand the question. Because like each primitive in Gaussian splatting has attached like spherical harmonics to it. Okay, and then.
But sometimes in some scenes, you can observe that the view-dependent effect is not encoded in the spherical harmonics, but actually it has some Gaussians behind the surface.
Okay, you mean that like it's impossible like this to disentangle the geometry from the appearance? Yeah, it's true, and I think with our model it can also happen. Like there's nothing that prevents that, so definitely it can be the case. Yeah.
Okay, thank you.
Unfortunately.
Yeah, thanks for the presentation. It's very, very interesting and a very nice study. But the last comment you made about the fact that I'm over here.
Oh, sorry.
The last comment you made about the fact that there may be overfitting.
Yeah.
I would have liked to see videos of free viewpoint. So I'm sure you've done it, right? So the question is, do you actually see? Is the visual, I would expect from the numbers, the visual quality to be better, right?
Yes.
Is that the case, or is it the fact that the interpolation actually degrades, so in the end the visual quality is not better or worse?
No, that's a very good question. Of course, like we try to evaluate it with different parameters, and like the results that I showed with the overfitting can like happen. Like if you would train them, they can overfit to the training views. But we also figured out that the kernels usually have like low frequencies, so they look more uniform, and I think they are not causing that many artifacts in that case. So, like, I mean, most of the times it's fine, but it's important to be careful with the training parameters.
Yeah, super nice presentation. I was just wondering, like, sometime what's interesting in like simpler form, like VMF and spherical harmonics, that you can get some analytical formula for integration, let's say against a cosine or something like that. So like it's cheaper to evaluate, but yours is kind of like global and high frequency. So when you do evaluate it against, let's say, an environment map or something like that, like is there a problem if you undersample your representation, or it's robust?
I mean, I'm not sure. We did some tries with like environment map fitting, but in the end the results were not good enough.
Okay.
So I think it can be problematic. But
okay. Thank you.
Yeah, thanks. I was surprised by the fact that you said your training times is 1.3 faster than spherical harmonics.
Yes.
So I'm surprised. Could you comment on that? Where does it come from? Because spherical harmonics, it's like basically inverting a matrix when you're projecting to compute the coefficients.
I mean, it's a much more simpler representation, of course, but I think like we are using class coefficients. Maybe that's the reason, but I don't know. It's like 4 times more compact representation. So, but yeah, I'm not 100% sure why.
Thanks.
Well, if there are no other questions, I have one actually. Yeah. So you did a whole evaluation of multiple spherical functions, some that existed already and whatnot, and somehow over the past like 25, 30 plus years, we always come back to spherical harmonics. Do you have an idea why that is?
Yeah, I think like when I started this project, I was wondering, of course I was like new to the field, so I was discovering everything and I was trying to understand. And then, I actually asked myself the same question, why I actually always come back to spherical harmonics. But I think the representation is simple and it's not very expensive to evaluate. It's easy to train. Like with this kind of functions, like it's more challenging. And maybe that's the case, but.
All right, let's thank the speaker again.
Thank you very much.